Okay. So now
we need out components.
Say it again.
Now we need out components.
We need this thing, basically.
Yeah.
And now we need that's the out components. Then what we need to do is just do
graph.
this.
Yeah. And you can even add a branch style to it. Although
No, I
actually
don't
it's
want
not
to.
branch style. We need spatial style.
Yeah, we do. What is that spatial style? How do we do that?
It's, let's see.
Put it in the chat.
Spatial graph. So you can do Wolfram Physics Project style data of special graph function.
Could you just put it in the chat?
Yeah. Right, and then you just
where do I put this?
The graph as an argument.
Oh.
The graph is the argument of the function.
Nice. Okay, so now let's do spatial reconstruction of check this works. Okay, actually I want to make that be default to 1. Okay, so let's try it. Let's say many more steps. Let's say 8. Well, that's interesting. Okay, so then let's say I do that for 2 steps. All right, so how do we understand that?
Well, can we compare it?
Yes.
And we might need a simple graph of it because having multiple edges doesn't really tell us much.
And we get multiple edges because why?
Well, because the pair of expressions can appear in multiple out components.
Doesn't simplify it very much, but a given pair of expressions.
Oh, events. These are events, not expressions.
Yeah, right. Did we do this correctly? You go back. The subsets are for a given event. Yeah, that's right. Right. It's for a given event. What are all the things in its future light cone? Right. And we're saying we connect all the things in its future light cone, even if it's a 2-step thing.
Right. Hold on. There are 2 steps, and let's see. Do we want the event only on the last layer or both layers? Probably only the last layer.
Yes, that's right. We only want it to go to an event.
Yeah, so then we need to filter them better.
Okay, let's do that. Okay, but let's take a look at what this looks like just to spatially reconstruct. Let's just do 10 steps, for example. That's a bit wild. So I wonder if we take a model that we understand well, why did it go to that one? What? Is that the wrong page there? That's the wrong page.
With the wrong picture.
Yeah. Well, that was uninspiring. That was equally uninspiring.
Interesting.
What's that?
Can you plot the causal graph, right? Oh, but it's given how many steps there are.
It's
probably
a knitter.
Turing machine like.
It's a knitter. Yeah, it's a knitter.
So that's why it looks like this. Yeah, so it's not surprising. There's only one event at the last layer.
So let's think about how space is knitted in a Turing machine, right? And what does that mean for faster than light travel in a Turing machine?
Yeah, but we have a problem with that function, is that if there is only one vertex in that component, it's not going to put it as a single vertex, disconnected from everything as a result.
Okay, let's figure out what the function should be. Okay, but I'm trying to understand, what is a Turing machine? What is the effective view of space in terms of a Turing machine? So in other words, gosh, this is kind of a mind bender, because basically what we're saying is the events make space. And we're asking the question, can there be events that essentially imagine we're knitting space and we're, preparing a piece of space using events, because that's the only way we can get to another part of space, is to use events to sort of prepare that part of space. And what we're saying is the vast majority of ways that we make more space sort of, oh boy, it's hard to understand.
Well, if we are preparing a state is a space once and we never visit it again, which I guess is not the case here, but if that's what you're doing, then causal graph wouldn't actually tell us about connectivity, because it's just after effect.
If we only visit space once, we got a tree in the causal graph.
Well, it is a.
That means we never
I'm
have
not sure if it's a
commutation.
tree, but it's close to path graph.
Yeah, we never visit something again.
Yeah.
Right? So let's imagine we have a Turing machine, that's something like a Turing machine, it's going back and forth like this, right?
And by the way, the causal graph, so there is a past space and there's a future space, which are not the same. So you might have, like, using our function, we can determine that there is some distance between something, and then they become disconnected immediately after, or maybe they already, okay, so let's say sometime in the past, they were completely disconnected parts of space produced. But the distance between them, according to this function, would still exist because, I mean, assuming we take sufficient number of steps.
So the point, so the argument here is the distance between points in between quotes points can clearly vary with time, but it's not even clear what we mean by points. What counts
events
as the same point?
Right, but that's not what I'm saying. I'm saying we can define the same function as we did, but inverse of it in time.
Yes.
So measure distances to the future.
Yeah, I understand. Okay, so this is a future distance measurer. So this is.
So this is past.
Okay, this measures distance relative to the past.
Yeah.
We could measure distance to the future.
Right.
Okay, we need to get this function right in just a second, okay? I'm kind of embarrassed that we've never made this function before because, we've talked about the qualitative picture that space, that distances are defined by these light cones, but we've never actually made this function. All right, but so roughly what's happening, I'm sorry, I'm still trying to understand qualitatively what's happening. So we make the space, something has made the space, and then we are, oh gosh, I'm so confused here. Look, maybe there's a way to think about this in terms of a causal graph that is fundamentally a grid, but has some, I mean, you've looked at these, there's basically a grid, but has some kind of perturbation to the grid. And then the question is, what does it mean? What does faster than light travel mean in, look, taking example like, I think we had a picture here. Where the heck is it?
So what kind of travel are you talking about? Are you saying there are already pre-existing connections which we are using? Or we are doing something like a warp drive?
No, I want a warp drive. Mostly I want a warp drive. Okay.
That pretty depends on the evolution out there.
What will?
The warp drive. Because it depends on what decides how quickly different parts of space evolve, depending, with respect to each other. Because one can imagine if it's not cause invariant and there is no restriction that one part of space needs to evolve with the same speed as the other one, then one updating order possible where just the warp drive will get updated and move somewhere and the rest of the universe won't get updated during the time at all.
Right. I mean, what you're saying is, during the time the rest of the universe is not being updated, the warp drive could do whatever it wants because nothing else will ever know. Okay, so the basic point is, all sorts of quotes motion is possible in a part of the universe that is being updated when others are not. But the whole point is that things knit together, so that is ultimately not possible. But that isn't possible because of the causal graph.
It depends on how they knit together.
Right, but the causal graph says generally this isn't possible.
So in a cause invariant system, it would not be possible. But it depends on the reason why the universe updates at the same time, because the other possibility is that it just updates this way on average.
What are you saying? What?
So it's possible that the reason universe updates simultaneously everywhere is because it's just the probability is highest when it does it. But
Well,
it
I don't think
doesn't
it
have to be the
matters whether it
case.
does it. It doesn't really matter. I mean, it's just a question of what the simultaneity surface is. What the most civilized simultaneity surfaces indicate identical, indicate simultaneous update.
Well, what do you mean? It depends on the updating order. Well, in some
I know it
cases,
depends. Yeah,
if it
I know.
works like my simulator of cell automaton, then it actually cannot update in different speeds in different places because
Right. It has to
it has
wait.
dependencies.
Right.
Right. But if it works as it just can update anywhere at any time, and it doesn't have those dependencies, then the reason it does not do that in real life is because it's unlikely. It just, if you have a random evolution order, for example, it would seem like everything updates simultaneously, but there's some small probability that it wouldn't.
Yes. Okay, but that's okay. That's a separate argument. Let's just talk about this case. Oh boy, I am so confused. I mean, let's okay. What's the right way to think about this? We can make a light cone. What does a light cone look like in the causal graph? And then, what does a light cone look like in the inferred spatial graph?
What do you mean? It's an out component.
This is an out component, but this inferred spatial graph is the overlaps between successive kind of open sets, right?
Right.
I mean, in a sense, this is a construction, this is like a construction of sets by looking at overlaps of space by looking at overlaps of open sets. Is that actually right? So the definition of topology. Is that a fair way to look at this? I mean, in other words, that as we define from every node, we're defining, well, I'm not sure. Okay. But okay, but hold on.
Well, I'm not sure what means for sets we open in this case.
Sets.
But other than that, yes. I mean, that's subset sets the same thing. That's by construction what we're doing.
Right. Okay. So let's go back through this again. We're looking. Okay. What is the speed of light in this picture? The speed of light, every single edge here, this is c times the elementary time, presumably. That distance is c times the elementary time by definition. Do you agree with that claim? No, it's not quite right. It's not quite right. Go ahead. What?
Well, more or less.
Okay, but this thing, okay, can we get the code right here? What do we have to do to get the code right?
Well, we'll just write, in the spec agent missing vertices, or okay, two problems. So first we need to find events in a range of generations that we want.
Yes. Hold on. I need to get a piece of food. I'll be right back. Okay.
Okay.
Second. Hello again. Sorry about that. Did you figure this out
Well,
by any chance?
well, so we need to add two variables in the beginning for events at two different generations, max and max minus dt.
Okay, so we add variables here.
Well, after the module, because we will need to use CAG for them.
Okay,
Well,
but
I have the names there.
What names are they?
Well, let's see. Well, the events at the layer max minus dt, which are start layer events and the end layer events, basically.
Okay. All right. So we do that before, we do that using CEG, right?
Yeah.
We're doing.
So you need to use the code we have is first mapped to our position, and they just have different conditions.
Sorry, here, we use this code here.
Yeah. To compute both of them, but conditions are different.
But what are we actually computing? We're computing a list of events.
Yeah.
Okay.
Which is what this is doing. For EV0, hash equals to dt.
Otherwise known as just DT. Right? Hash equals DT is just DT there, right?
Yeah.
Okay, and EV1.
And EV1 is just position of max CG.
Okay.
Oh, wait. It's CG equals to max CG, not the whole expression there. So it's 0. Hold on.
It's 0 there.
Yeah. I mean, it would be much clearer if it just had position of CG equal max CG.
It's that's fine because okay. Now what?
Okay, then the one on the next line should be EV0. This whole expression starting with first. And now, so after let's see. Yeah, so from each of these lists, we need to select only events that appear in EV1. So I guess we can map cases over it. These alternatives EV1.
Right. So in OC, in each one of these, we say cases in here. Actually, why don't we just say we just want to delete? We want to keep only those things which are present in that list.
Yeah. I mean, you can say replace, every.
No, let me just say select member queue. I never remember even after all this what the order of member queue is.
Well, it has a form. What is this? Operator form. So you don't need to
remember it. So that's AV1, right?
Yeah, and it's on the second layer, I think. So select. the second level.
Is the
Because
select
these
that?
are lists.
Yeah. Okay, so we have to do that select. We have to map the select onto this, right? Each one of those wants to be on the list, right? So we do map the select onto that.
Yeah.
And it's that whole thing.
Wait, what? If you have EV0 outside of everything, then we don't need to map select.
Oh, we can. No, you're right. We just say that rest, right? Comma.
Yeah.
And we close for the select there. We get rid of the parens. Okay.
Okay, let's see how well this works first. Although actually, okay, work it out.
That wasn't very good. Okay, what would you like to see here?
Well, let's see EV0 and EV1 first. Let's see EV1 first, okay. It looks reasonable.
Okay. So, out component.
Let's see what rests of, yeah, put an echo in front of rest. Okay, and that should be a member of EV1, which it is.
Where's EV1? This thing here, right?
First one is EV1, yeah.
Okay, so let's look at the selects then.
Maybe using member incorrectly. I think member operator form takes which one should be the member, not the list. So it should be hash, comma.
No, it's member this thing.
Yeah. Right.
Okay.
Yeah, and then as a first argument of graph, we need to add EV1. And there's one echo left in OC after select.
Okay. Now let's look at the 2 case. It's pretty much what we got before, isn't it?
Well, can we reevaluate this one? It should have fewer vertices now.
Oh, it's not quite the same. It's not the same. Okay. All right, let's delete these and we'll reevaluate. Okay. All right, so what can we conclude from these? So we can do a dimension estimate on this, for example. Right, just like we can do a dimension estimate. Let's look at this one. Okay, so that's somewhat comparable. Okay. That's actually interesting because that's actually not totally crazily different from what you get by running the actual thing.
Yeah, I think so.
I mean, really, let's run it for 8 steps because that's sort of a...
What's wrong with 10 steps?
Because I don't think it'll be comparable. I think it's more comparable at 8 steps.
But the events displayed here are from maybe 9 steps. Because the events are in between the 9th and the 10th steps.
Okay.
Yeah.
All right. So this is a reconstruction of space. Now, so where's our dimension estimator? Just for fun, we can compare the dimensions of these two things. But also, okay, what does a light cone look like? In here, a light cone, how do we draw a light cone in this? We start from a given event, and then we're simply looking at the out component of a given.
Yeah.
What are the things
we can do
in
it
here?
fairly easily, actually.
Oh, wait. Are these events here?
Yeah.
Those nodes are events.
Right.
So in fact, this is a graph. What we should be doing here is we should be using the event. The nodes here are not atoms of space, they're events.
Yeah.
So actually, let's redo the formatting of this graph to show those as events, because these are connections between events. These are spatial-like connections between events, right?
Oh, I see. You need different vertex style.
Yeah. So what is the vertex style there?
Let's see. Oh, I guess it's causal graph vertex style.
Okay, so should I just use...
So there is... I guess you can use a function,
Well, I can use the function and then put another thing outside that.
Yeah, well, sure. Yeah, so you need vertex style goes to Wolfram Physics Project style data of causal graph, vertex style.
Can't I use the... I'd be using the function repository version of this?
You don't have to, and now you have syntax completion if you don't. Okay, so you don't like syntax completion.
I love syntax completion. I just...
Like if you tell me how to put it in the resource functions, I will, but
well, ask somebody other than me. I'm just the freaking CEO. I don't know these things.
I don't think it's possible. It's a bit of a hack already.
Okay. What am I doing here?
Causal graph and then vertex style.
An interesting new graph type. I haven't seen one of those for a while. Okay. so then this is to be compared. So that is a bunch of events. Okay, cool. All right. So, God, this is a relationship between atoms of space. This is a relationship between events, right? Now, here, the light cone, starting with a given atom, right? We can ask kind of,
what do you mean starting with an atom? That's not very well defined. The same atom can appear in many places.
well, a node in this graph, right? That's an atom.
Yes, but it might appear on multiple layers, on multiple steps.
Yes.
Why don't you start them with events?
No, I understand that, but I'm asking if I'm trying to compare. Okay, what we've done in the past is we've asked if we change one atom, what effect does that have?
What do you mean to change atom? Atom, by definition, is not changeable.
No, I know, but
Then
from
you
the
need to change expressions, not atoms.
okay, from outside the system, you make a change,
Okay.
right? Then you can do that. You can ask what effect does that change have? But I agree that it makes more sense to change an event here.
Right,
Okay.
event or expression. I mean, you can start causal graphs with either events or expressions. You can use expressions, events graph for that.
Okay, so what you're saying is, okay, so hold on. We're making a change. The issue is a change in event here. Boy, this is confusing. Is it the case that, okay, there's a geodesic ball that comes out from that event. We change this event at one step, and we ask on subsequent steps, how does it change? What is the thing affected by the change event? Is that right? Is that what we're doing? I don't even know how we plot that. We just label that event and we say what events are in the out component of that event.
Well, here it's a spatial plot already, so it's just going to be a subgraph here.
No, I understand it's a subgraph, right? But so let's okay, so this is light cones.
I mean, we can plot very easily.
Yeah, let's do it.
Because the vertex names here are the same as vertex names in the causal graph.
All right, so let's look at the causal graph here. Layered causal graph, right?
Yeah. You need to call it as a prop from the evolution object. Put a closing bracket after 10. Yeah.
Okay, so the things that we see here are events from level 8 and 9. Is that correct? Or is it only from level 8?
Yes, it should be.
Okay, events.
No, only 8.
Shown here are from level 8. Okay. So that's showing.
I'm not sure it's the same as level 8 from this top, because
Why
It
not?
might be one less than that. Because these are events instead of expressions. They're in between
Okay.
levels.
So it
But
might
it's
be
definitely
more.
level -2. No, the causal graph should be 10 layers because it's 10 layers on the bottom. I'm just saying.
Okay, are from layers, but these are the events, right? So which events
Right.
are they that are shown
It's
here?
layer -2 or hold on, -3.
Okay, let's do the
Which,
following.
let's see,
Let's do
1,
the
2,
following.
3,
Let's
4,
let's
5,
let's do the
6,
following.
7, 8. Yeah, they are level 8. Okay, never mind.
Okay, so I'm going to say level here, and I'm going to say vertex labels. Oops, graph. Well, actually, I can just put it in here.
Oh, it should be 8.
Okay. All right, that's those. All right, now here, I want to say graph. Okay, I am utterly confused. Why are those numbers 400 and things?
Good question.
Let's do the corresponding thing for 5 steps and one thing. Okay.
Oh, wait. Yes. Yes, this I went from level 10 because we wouldn't know how to connect events at level 8 yet. Yeah, so it's actually correct.
Okay, so here 18 goes to 17. Why is 18 connected to 17? Because if we show it on one more level here.
Yeah, because 8 connects to both of them. No, you don't need one more layer. It's this events from the last layer on the graph on the bottom.
Oh, I
So
see. So wait a minute. So wait a minute.
8 goes to 17 and 18. And so is 9.
I see. Okay. So, okay. So this is the causal graph.
Yeah, so it's all correct. We just needed to plot it for
Yeah,
10
right.
steps instead of
Okay.
8.
Okay. So this shows the events from the final layer that are connected through events that have common ancestors and events that have as common ancestors events in the previous level. Right?
Yeah.
Okay, so up here then, the full version, the version of this should be, what level is this now?
10.
I don't want to plot 10, I'm going to just plot 8. And then this would be, the analog of that would be 8, right? And then that's the bottom level of 8, right? And so if we plot it at one level, okay, and at 2 levels, so that's 105, so that's things here which didn't have common ancestors for 2 previous steps. So there it is from 2 previous steps. So eventually, if we were to go 8 levels here, no, that must be wrong. Maybe it's 7 levels. Yeah, right. At 7 levels, everything is connected to the Big Bang.
Right.
Okay. Okay, so now what do we conclude from this? So now this gives us a way of reconstructing space that we are to compare to, I mean, again, we're to compare that to what we get by just looking at the final state plot here, right? Okay. Now, so we can look at geodesic balls in here, and we can look at what does a geodesic ball in here mean? Anything? I mean, if we look at it just on this graph, what does it mean?
Let's see. Well, it's in approximation to the intersection with a causal cone, but not quite.
Right, okay, so let's look at a geodesic ball on this. So this would be with G equals that, highlight graph, G comma subgraph G, vertex out component of G comma, pick a random number. What number is, what would we want to pick? Let's pick
91.
Okay.
Oh, we need a number from previous layer though, so that's not going to work. Yeah, let's look at the causal graph again. Well, we can pick 28 or 15. Wait, hold on. It's vertex out component not in this graph, but in the causal graph.
No, but I want to know in this graph itself.
Yes, I know, but it's out component of a causal graph, but the subgraph of this one.
Okay, that gives the genuine light cone, but this is a fake light cone. This is a light cone where you're just looking at space.
Oh, I see. Okay.
Right? This is the fake spatial light cone. This is the light cone that you would reconstruct purely in space, I think.
Well, it's not a cone, it's just the ball.
Yeah,
it's
right.
Intersection with that
Right. This is what you would think just looking at the reconstructed structure of space, as opposed to the actual cone. You see what I'm saying?
Right.
Okay, so the actual light cone. But now, what's the relationship between this fake cone and the fake cone in here?
Well, it's kind of the same as relationship between the graphs. It's reconstructed one. I mean, they might be very different in some cases, because
yeah, I understand.
Again,
but
shared atoms doesn't imply their shared events. Although shared events usually does imply shared atoms unless the rule is disconnected.
Okay, so let's understand that relationship. Okay, so here, okay, so relation between light cones in or light or between balls in the spatial graph and the reconstructed spatial graph. So those we believe will be very similar. And the question is, how do those relate to the light cone balls? Okay. Then relation to light cone balls. And that's where we get faster than light travel. Because if those don't agree, the balls in the spatial graph are our experience of space. You see what I'm saying? The light cones are where you can actually reach. Does that make sense?
Hold on, let me think again. So the light cone is a real one.
Yes.
And this one is apparent one.
Yes.
Well, it does sound right.
Right. So let's look at, okay, so this is the reconstructed or fake / apparent spatial cone, light cone, as opposed to the genuine light cone. Right, okay, so let's look at what the genuine light cone is. Okay, so that's this, but instead of being a highlight graph from this, it's a highlight graph from the causal graph. What is it? Is it that 8? Where is it the causal graph from?
Well, 8 steps is sufficient.
Okay, but there's the vertex component from what node?
Well, some node above 91, which you need to check there. Let's see, 91 is on the left. And
Say 26.
so it's 26 or 27. You need to say causal graph in the Wolfram over here. Yeah.
Okay. All right, let's be more systematic about this. By the way, that could be 3 steps there. Wow, why is that not doing anything? Oh, because it doesn't.
Well, because it's 2 steps away.
Yeah, it needs to go to 9 there.
But events from 9 are not on this graph.
Right.
You need to select something earlier than 26.
Right, so that's the vertex in component of that.
Yeah.
It's at layer. Okay, so let's be more systematic. Let's ask the question. Okay, so here, okay. Comparison between light cone, between genuine light cone genuine light cone boundary and, well, it's really the shadow of the light cone, between the genuine light cone shadow and, what is the inverse of a shadow? Conic section. What is it? What do you call the thing that's in the conic section when you
I'm not sure.
light cone section and the inferred effective spatial region, right? That's what we want to compare. the genuine light
Yeah.
cone slice region and the inferred effective spatial region. Okay, so let's figure out how we do that somewhat systematically. So this is,
We can do all of this on a normal spatial graphs.
you mean plot them?
Well, I'm saying all of this business is comparing balls and sections of the light cones. We can do all of that on normal spatial graphs.
How?
Well, because we can make a light cone through an expression events graph and get expressions and then highlight those expressions in Wolfram model plot.
Okay, fine. Let's do it. Okay, so then this is, okay, so this is light cone slice. But what do we need to know for the light cone slice? We need to know the initial event, right?
Let's see. Well, we need an object, initial event, and the step number.
It's going to be a nuisance to deduce that initial event. We'll worry about that later. I'm going to call this light cone 0 because I think that initial will want another function that deduces the initial event. And what is the step number? That's a t, steps, right? So that's the light cone slice. And then this is now the effective, the deduced spatial region, spatial ball. Is that right? And for that, what
you mean that's an ordinary spatial ball? Why is it deduced?
Well, I don't understand why this is, this thing that we're computing here is distance between events. We can do this both things for events, right? We can either compare an events, we can either compare a bag of events or a bag of atoms of space.
Expressions.
Okay, i.e. hyperedges.
Right.
Okay. And in the limit, these are going to be the same, but we can either compare how far we got in terms of events or how far we got in terms of hyperedges.
Yeah.
Okay. And okay, from a given point. Now that point, you know, starting from a given point. But that point is what are we saying here? How do we compare those 2 points in the 2 cases? So starting from a given point, which is either an event on a previous step or some successor of that event
Yeah.
in the
Obvious.
target time step, in the target slice. Right?
Yeah, I guess, I mean, we could in principle select a center of the region we'll get as a light cone intersection.
No, but we can just pick an event on a previous step, and then we simply ask, you know, we'll pick a random event on this step, and what we're going to compare is either the light cone of that event, okay? Compare of that selected event, or compare the effective disk, so to speak, of the successor of that event. Which successor of that event?
Well, exactly. So I'm saying one way to determine the closest successor is to take this light cone intersection and find the middle of it.
Yeah, okay.
I mean, we could select one at random, but then there's a chance we'll end up at the edge.
No, e.g. from the middle of the light cone. So that could go wrong, but in a non-pathological case, that's going to be okay.
Yeah.
All right, so let's do this case. So this is first, let's first of all do it from the bag of events. We could also do it from a bag of expressions. Right, where the initial expression has a future light cone which intersects with another time-like, with another space-like slice. Right?
All right. Say it again.
Okay, so look, case one. Hyperedge. Points are approximated by hyperedges. Case two, points are approximated by events. See what I'm saying?
Yeah, so that's why we have two different graphs.
Right. Now, true points might be atoms of space, which is yet different again.
Well, I'm not so sure about that.
What's that?
Yeah, you care a lot about these atoms, but in my view, atoms are just for matching purposes. Because atoms is the same atom can appear on different layers, simultaneously, and it's
Max,
very
you
hard
are,
to deal with.
yeah, and I understand. So you're, well, but the fact that they can appear on multiple layers is the statement that atoms of space have a certain degree of permanence.
Sure.
Look, you are simply made at this moment of some number of, 10 to the 90th atoms of space, which are
or expressions,
or escaped bound variables and lambdas. We are but a pile of escaped bound variables.
Right. Well, I'm just saying expressions are easier to deal with than atoms.
No, it's fine. So case three would be points are approximated by atoms, by elements. Okay. Okay. All right. So let's look at these cases now. So let's do, which one should we do first? Should we do hyperedges first?
Okay.
Okay. So let's do case one.
It seems to be the most natural one to me.
Okay. So how do we do it? So we say, pick a hyperedge, right?
Or in event.
Right, we're not dealing.
There's a start of the light cone.
I know, but I want to pick the everything. Let's do everything in terms of hyperedges or everything in terms of events. So the start of the light cone is a hyperedge.
Okay.
Okay. So start of light cone is a hyperedge. Okay. So how do we get the hyperedge from one of these things? So we say,
well, we can use expressions events graph. To get all of them. And then you can do out component in it as well.
Okay, so now what do we do here? So this is an what the heck is this thing again? This is, so
Blue
every
ones are
node,
expressions.
yeah, blue are expressions. So let's show this in a
In my opinion, that's the most useful graph of all of them. It shows you everything.
right. Is this going to be horrifying? What's going to happen here?
Not too bad, I mean. It just tells you, yeah. Wait, I see you. Okay, so let's just tell you the numbers. If you do vertex labels goes automatic as an option to the property instead, it will tell you the contents of expressions instead.
What do you mean there? So here in this, what are you saying?
Yeah,
Expressions
so make an object and then add an option to this property. Vertex labels goes automatic.
like this.
Yeah.
Okay, so those are the, okay, so so these are the atom numbers, but now what does that,
Yeah.
and that event, okay.
But it doesn't help you with plotting, I mean, with figuring out the start of the light cone, because then you need the numbers.
Well, these numbers here, those are the numbers here.
This has the numbers of atoms.
Oh, I see.
Yeah, you
This
can do vertex labels goes to name instead, then it will give you
numbers of atom, number of this includes the atom number for in each expression.
yeah.
Okay. All right, so vertex labels goes to name, gives this somewhat messy thing, which gives a minute. Why is that
Maybe
expression
another
5?
option here, which will just show the numbers. Oh, what's
Right.
wrong with it?
No, I'm
It's a
sorry, but I
fifth
don't understand.
expression.
Yeah, but hold on. We can just do this. Hold on. How do we do the mapping?
Mapping over
Gosh.
what?
Well, here I
Over
just
labels.
I just want to say with G equals with WMO equals this thing here of WMO of expression events graph. Actually, I want that expression events graph, don't I? And
I'm
then I
not
want,
sure what you're trying to do. I mean, you call a variable object.
okay, hold on. What I'm trying to do is this. Yeah, this will work. Let's call this G. And that wants to be the expression events graph. That's what I was trying to do. Right? So now that has, but I don't understand why these expressions,
The indices of expressions.
I see, I see. Those are the expression indices and those are the contents of the expressions.
Right. But we don't really care about contents here because
No, we don't.
code,
We only care about the
yeah.
indices. Okay, so now what do we do here? We say, all right, so what we're trying to do is we're trying to get the, given an index of an expression on one of these levels, we're going to pick it and we're going to say, you know,
Out component.
we're going to get the out component of that.
Right.
And then, so pick an expression at a particular step. Okay, then what? Then
well, compute out component.
Then compute its out component to get its light cone.
Yeah.
Get its genuine light cone.
Yeah. Then figure the intersection with a layer.
Right.
On the plot.
Right. So let's actually do that for this case. Okay. So let's say here, let's do this. Let's say this thing here, and then let's say with GG equals this. And now let's say highlight graph GG subgraph GG vertex out component GG comma, what would you like? Pick 8, let's say. Should you do that?
Okay.
Oh no, it's not at 8, it's expression 8, isn't it?
Oh yeah. Right.
Is that going to work with vertex out component, or is it going to get confused by the fact that it's a list?
Well, it might need another list, I'm not sure.
Okay, so that is showing the genuine future light cone, right? Okay. Now, what we want to compare with, oh my God, how do we do this? So then we pick a destination event here. We pick a destination, like one of these expressions, like 27, let's say. Okay, what is the effective graph at the end here?
I'm saying effective.
Well, I mean, the other way of doing this, right, is to reconstruct the structure of this final graph by using those things there, by using the one layer light cone, right, to reconstruct the instantaneous.
Well, that would be completely disconnected every time, because each expression only has one creator event.
Okay, what were we doing before? How were we constructing this?
Well, we had a causal graph, So we need to take 2 layers at a time here.
Well, what about just taking the final?
Well, we can do it here. Just we need to skip layers with events, and when we look 1 layer into the past, we need to jump the next expressions layer.
Okay, hold on. I'm trying to understand, how do we get, okay, in this way of looking at it in terms of expressions. Oh, I see. Some of those expressions are actually connected to each other by virtue of the fact that they have shared atoms, right?
Yeah.
Okay, so that's what we have to show now, is which of those things are connected because they have shared atoms. Okay. So
Right,
how do we
which is
draw
just Wolfram model plot.
of that final state?
Yeah.
Okay, but I'd like to show on this picture.
Well, actually, it's not quite Wolfram model plot because you want a complement to it.
Why? So, I mean,
Because this is expression vertices, not atom vertices. So you want to have edge between expressions if there's a shared atom. So in Wolfram model plot, you want to switch vertices and edges.
okay, hold on. So how do we do that? So we'd say, okay, now construct the final version of space based on expression knitting, so to speak. Expression connection by common atoms, by common elements, which is the dual of the usual way of doing it.
Yeah. Well, okay, so we need to first get the contents of those expressions.
Okay, how do we do that? What is it? Is it called expression? What is it called?
So where do we get the list of expressions indices from? I mean, the property one is all expressions that give you the contents. And then you need to take part of it corresponding to expressions you want to get.
Okay, so all expressions, there we go. So these are the expression indices 35.
Yeah.
These ones here. So how do we get that light cone? That's the out component of expression 8.
Well, there are expression generations property as well, similar to events generations.
Yeah, but look, this is what we want ultimately. This is what we want to get. We want to get the expression. Where's GG? GG. We don't really need, we just need the expressions graph. What is the expressions graph here? Do you see what I'm saying? Is there a graph of expressions?
No. I mean, no.
Well, the only thing is expression events graph.
Yeah, there are no graph of expression. I mean, there are no complement to it.
Okay, so the expressions events graph. Expression, what is it called? Expressions? Oh, expressions events graph. Okay, and then we want to select from this.
Expressions as the last layer. So there is edge generations list property, which gives you generations of expressions.
Say it again.
Edge generations list.
Edge?
Yes. Need to clean those names up right now. I mean, edge refers to expressions in this case. Yeah,
Okay,
so you take positions of 4 here.
but
Or
position
positions of the
4
maximum.
in this here.
No, in the generations list.
Okay. I don't really understand why I'm doing that.
Well, because we need to take expressions only from the last layer. And this tells you which layer each expression belongs to.
Okay. Okay.
Right, and now we need, from the previous list, we need to select all of these expressions.
This list here.
Yeah.
Okay. All right. Okay. So with t equals 4. What am I doing now? I'm doing.
Yeah, so cases in this list of basically expression comma alternatives of the list below.
But what is the point? I'm just going to get a list of things here, a list of
List of
expressions.
expressions, and then you can use all expressions property to figure out the contents of those expressions.
Okay, let's write this in a cleaner way. Okay, so what is this object that we're defining here? This is the effective spatial ball. Okay, and we have a Wolfram model object, and we have an init. We have an event 0, and we don't really need the t, do we? Because the t is deducible from WMO, correct?
Yeah.
Okay, so let's write this now. So what do we do first? We say, so first of all, let's do a module, let's do a with t
Let's get the
equals,
T.
yeah, what is t?
It's total generations count. Or complete generations count. So in this case, most cases would be the same.
Okay, now what? Now we get, okay, so here, my God, what is this now? So this is this thing.
Actually, hold on, maybe there's a better way to do it. Actually, yes, this is the wrong way to do it. Because some expressions might remain from the previous layers and the last step, like expression 20 in the graph. So
Okay, all right, fine.
we need a smarter way. Hold on. Let me figure out what it's called. Okay, state edge indices after event.
So here, wait a minute, where are we doing that?
Yeah, so to get this list of the final state expressions.
State edge indices.
After event,
like
and
this.
the second argument is -1.
Okay.
Yeah.
And so what do I use that for? Where does that go?
So that gives you final state expressions.
Is that the alternative to edge generations list or what?
Yes. Yes.
Okay, so I just do that here. Is that right?
Yeah.
Okay. All right, now what? So that's the final expressions. That's the list of these expression numbers, right?
Yeah. But I need to name it something. And
Okay.
need to put a module instead of a piece to do this.
Okay.
Okay, now I guess you need the out component.
Which is from where?
Which should be correct from the two cells above.
Okay. And that there will be, that's the initial event.
Is it event or expression? Well, I guess you can use any of them, doesn't.
No, what is it? It's an expression actually. X per 0.
I mean, in this format, either of them will work.
Yeah, but I want to use expression. Okay. X per 0. Okay. So that gives us the out component. And so now we want the intersection of that with fxpers, right? Am I
Well,
correct?
it's not an intersection because the vertex names here are different. They have expression prefix.
In which one?
In the vertex names in the out component.
Okay, so I can just say last of that.
But now some of them are events. So you need to select or cases of those which are expressions and then last.
I don't need to do the last because I can just say cases of that,
Yeah,
comma,
right.
expression of n blank arrow n. Okay, that's the cases there. Oops. Vertex out component of that.
We are delayed.
Okay, that's for the cases. Intersection of that.
This fx plus.
Okay. That's going to tell
Yeah,
me.
let's actually run it and see if it works.
Okay. Of. Okay.
Let's see. 20. Yeah, looks correct.
Twins are two offspring produced by the same.
Okay. Yeah. Well, that is a ball of expressions.
Just 1 second, 1 second, 1 second. Okay, say that again, what?
Well, that is the ball, expressions in that ball.
Okay, but now we need to know.
Now we need a graph. So we can make another function, which is like expressions connectivity graph or something, which will take an object and a list of expressions.
Right. But don't we just want to know? No, don't we want to just have the expressions version of the spatial graph? Don't we want
Right.
another thing?
Right, but we need to tell it which expressions to use for it.
But why don't we just use the expressions on a particular time step? Not the ones that came from a particular light cone. Right? Expressions,
Oh, sure, we can do it.
spatial graph. And this would be a WMO, and that's it. It just has a WMO. Right? Because it's going to get the...
Right.
Okay?
Okay.
So what do we do? So we just get, from that WMO, we get all the expressions on the last step of that WMO. Is that this thing here? What is that?
Yes.
It's this thing here?
Yeah.
Okay. Okay, so now what?
Okay, now if we, so all expressions tells us what the atoms are. So
Hold on one second. Sorry, so now what do we want to do?
So we can get contents of expressions using all expressions property. Yeah, so these are indices.
Right. So WMO of all expressions.
Part of IX. That's contents.
Yeah. Okay, so that's the expressions.
Yeah, and then we need to build an index for those, basically. For, let's see.
Well, let's just look at.
So we need to make IX rule this threaded, that we have index of expression to the content.
I see. IX goes to this, and then we thread that. Okay,
Yeah, and then we need to thread each of them, reverse it, and then turn it into association and merge them, so that we get atom to list of expressions.
Okay, now what do we do with this?
So let's thread each one. So
what you want to do is you want to get 2 goes to 30. Is that correct?
Yeah. Yes.
Okay,
yeah. Actually, let's do WMO to AX, right?
Okay, so the first is a thread of that, and then we want to map thread onto that.
IX. I is missing.
And then we want to concatenate that list, I claim.
Oh. Do we?
I think so. That gives us a mapping from of which.
But we need to merge them.
Okay, hold on. Well, let's look at it without the concatenate, because then you maybe understand what's going on. Okay, that's those. Now, what do you want to do?
So, let's see. Well, we can turn each of those sublists into associations and merge them so that we get atom to a list of expressions.
Okay, so each
And
of the,
once, yeah. Don't we need to map as okay. Yeah, then merge them. I think just default merge would do it.
what?
No.
Wait a minute.
Okay, I guess we need to say list or identity as a second argument. I think we need probably identity. Yeah, identity, because now it has double list. It's list already.
Okay.
Okay, now we just need values of that, and then we do the same thing as we did before. We take subsets of two elements, make complete graphs from each of them. Unless you want to treat it as an undirected hypergraph, which it is.
No, I don't particularly. Let's make graphs out of it. Well, let's treat it as a hypergraph. It makes more sense that way, actually.
It would probably look nice as well.
Okay, so then that's this. Okay, so then there, that's that. Okay, now how do we visualize that hypergraph?
Well, it's Wolfram model plot, but you will need to adjust some settings here.
Okay.
I think I have a neat example of documentation. Okay, here's one.
That was a hypergraph to graph that I just did there.
Yes, but you can plot it as an actual hypergraph if you use these options that I sent to you in chat.
Okay, so this is so what we want to do here, what is this? Is this an unordered hypergraph or something?
Yeah.
Kind of swank. Okay, so now on that hypergraph, we need to indicate the effective spatial ball, right, deduced from a particular node. You see what I'm saying? And then we compare that with the expressions that were reached over here. See what I'm saying?
Right.
So like if we were to say here, just for jollies, we were to do a slightly bigger version of this. I'm amazed we've never drawn these before, by the way. This is actually a pretty cool object. So if we were to label this,
It's not a graph.
what's that?
It's not a graph.
That's a problem, isn't it?
But you can label it anyway.
How?
The vertex labels option in Wolfram plot.
Okay, so this is labeling what? It's labeling expressions, right?
Yeah.
Okay. So what we've got here okay, so what we have to compare is this light cone with what? With a thing we get to by going a certain distance out in this hypergraph, right? So we need to know, how do we draw a ball on this hypergraph? Do you see what I'm asking?
Well, I think we had some resource function to hypergraph neighborhoods.
We do, yes. We do. Let me find that. How come we never have drawn these plots before? This is embarrassing.
Yeah, we probably should add property for them.
Yeah, well, you can do that from this. Okay, so now what are these what is this called? So connected hypergraph neighborhoods. There we go. First neighborhoods of vertex 3. Okay, so this is now this. So we would then say hypergraph neighborhoods of expression, this thing here. Now we have to say of vertex number 3, let's say, to 2 steps. The hell is that? What are those? All neighborhoods of hypergraph. What does that mean? What is that? I don't understand what that is. All neighborhoods of a hypergraph.
Up to a given distance. Well, it doesn't have vertex 3 in it, I guess. That's one problem.
Oh, I see. So let's do vertex 111. There we go. But now,
So we can now get all the vertices from here, and we can highlight those.
why is there comma 2 here? All neighborhoods up to distance R.
Yeah, so we just need the last of it. Because I guess it's distance 1 and distance 2.
Well, is that right? Is that what it's doing?
I think so.
Yeah,
And
okay, fine.
the first one appears on the second one. In the middle.
Okay, so you're saying we get last of this.
Yeah.
And then we get the vertex list.
Vertex list.
And now we
Yeah, so
highlight
we
that
can
in here.
highlight vertices right away. And to highlight the hyperedges, we'll have to find them.
Right, but how do we highlight the vertices?
So let's see. I think we just highlight, graph highlight.
Well, highlight graph, but
Rule
it's
list
not a
versus.
graph. But it's not a graph.
No, graph highlight, not highlight graph, as an option.
Oh, I see. For what?
Well, here, for another hypergraph plot. Graph highlight goes to list of vertices.
Okay. All right, so let's do a slightly bigger version. Okay. So what we have to do so this is what we're comparing. We're comparing the light cone that we actually reach with this thing here. Right? So this was with vertex 111. So the analog of that is we take this thing here Okay, this is an 8-step, that was a 6-step thing. Okay, so let's go 6 steps here. That's a big light cone. So let's go to a smaller light cone here. Let's go to the vertex 10.
It's event 10.
Event 10 light cone. Is that, am I pointing to an event? Or,
Yes.
But why did this was an expression? That's an expression 8 light cone.
Yeah, you can start from 18 to be equivalent to event 10.
Okay, so expression 18.
Yeah.
You know, I just noticed a bug.
What is it?
If I resize a graph,
Oh, I know that, yeah. It's
I resize a graph
already.
in, no, it's not for you. If I resize a graph in the,
I think it's specific to expression events graph or graphs in set replace. I don't think it's
oh, is that right?
issues graph in general.
Okay, fine.
Yeah.
Okay, all right, okay. Oh, because you have some absolute size or something in it.
Well, I don't. I mean, I don't know what I have. I didn't look
Okay,
into
all right,
that.
okay. So anyway, there's the light cone. There's the genuine light cone, okay? Now let's look at the effective let's look at the effective structure of space down here, right? So that will be given by but now we need to have a graph highlight there. So this is the effective structure of space is given by this. But now the graph highlight, we pick one of these nodes here. What would that be? Like one of those things there. Let's say 141, right?
Okay.
And let's just go one step there. Okay, so what the heck are we concluding from this? How many steps do we go here? How many effective steps do we go here? 1, 2, 3 steps, right?
Yeah.
So really what we want to do is we want to go the 3-step version of that.
But there's a different kind of steps, no?
Well, how do we know how much the same amount of time was? In that amount of time, how far did we go? The time is the sequential number of events we do. So is it 2 steps or 3 steps? See what I'm saying? This is to go from here, that's 1 step, 2 steps, 3 steps. It's 3 steps.
Right, but whether they correspond to 3 steps on this graph depends on things like rule size and so on. Because event might jump more than single expression at a time. And you can see here, it looks like it's much larger than the one there.
Well, let's count how many events there were here, right? So this thing here, how do we know how many events there were down here? Because that's the size of this light cone, right? That's what we have to. That's what we have
how
to
many expressions are highlighted there?
Yeah, that's right. So what we need to compare
Well, we
is,
have a function to.
okay, but what we need to compare is the number of expressions here, right, with the number of expressions we reached here.
Yeah.
Because this is the genuine light cone, and this is the fake light cone based by knitting things together at the final state. Right? And it's the difference between those two things that gives us the effective speed. Right? That tells us whether there are things that can go, because this is our deduced structure of space.
Yeah.
And the above is our deduced structure of space based on local crisscrossing at a particular step, at a particular slice in the foliation. Right? That's what that is. That's what we get by just doing this little crisscross, synchronization things at that step.
Yeah.
Right? So now what we need to do is take those events. Yeah, all we need to do is take that list of events and literally compare it, plot it in this picture, and see whether it's the same. That's all we need to do.
Right.
Now, it might not land in the same place, but we can compare them, right? To get a sense of whether this is the genuine light cone, though it may not be centered in the same place. Okay, so how do we get that list of events down there?
Did you have a function for it?
Is that it? The effective spatial ball?
Yeah, I think so.
Hold on. So this is, okay, this is the function to deduce the effective spatial ball from the genuine light cone. Is that correct? Is that what that is?
Yeah,
Okay, function to construct the effective spatial hypergraph from events. Okay, so
why from events?
from expressions, I meant to say.
Yeah,
Okay, so now down here, what we want to do is we want to say this thing here, right? But now we want a predecessor event. What did we use for our predecessor event? Predecessor expression. What was the predecessor expression that we used to get this? It was expression 18, right?
yeah,
Okay, so now here, drum roll. Okay, and they're somewhat different. Okay, so let's quantitatively compare. So what we're comparing is this list here. Right, what was that 141 doing? Oh, that's the hypergraph neighborhoods from here. Because we don't know the successor.
yeah,
What the hell is the success? They're all successors of 18.
right.
Right. These are the, quotes, genuine successors of 18, of expression 18. Any of these could be the center of the ball in the effective spatial hypergraph.
Right. Or we can take this genuine hypergraph, convert it to a graph, find the graph center, and plot the ball from there.
Yes. Okay. All right. Let's do that. Okay. Okay. So now,
Well, first you need a sub-hypergraph.
how do we get that? That's just, the heck is the subhypergraph? We're highlighting those.
Well, we find all the vertices. Well, we have list of vertices. So we find all hyperedges which contain those vertices. That's all.
Okay. Do we have a subhypergraph function?
I don't think so.
You do or do not?
I don't know.
Okay. All right. No, we don't seem to have. Okay. So then what do we want to do? We want to say subhypergraph of hypergraph, and then we want to say, what do we want to say here? We want to say, what are these? Those are vertices, right?
Right.
Okay, so if any of these edges, what do we want to keep? We want to keep those edges which contain any of those vertices, right? Is that correct?
Right.
So I want to say select in H. And it's the same.
Wait, any vertices or all vertices? Probably all vertices.
Sorry, what are you saying? In which
All
all
they
vertices
contain all vertices, not any vertices.
You're saying where this list, where a vertex, where one of these things here is contained, where every element in here is contained in here. Is that correct?
Yes.
Okay. So all true in that thing of member Q. Am I going to get this the right way around? Member Q.
Member Q vertices, comma, hash.
The right way around?
Yes. And all true is correct. Yeah.
Okay. So now we say sub hypergraph of let's call this subhypergraph of that, comma, that effective spatial ball. Okay?
Right.
So now what do we do? Now we say hypergraph to graph. Is that right?
Yeah. Right.
Okay. Now that's a directed hypergraph. Is that what we want? Is that a directed graph? Is that what we want?
Hold on. That's a weird graph. What does it do exactly? I think we want to turn each of those hyperedges into a complete graph. I don't think it's doing it. Yeah, I think that's a different kind of graph.
Yeah, it's a different kind of graph. Okay, so to turn those into, so this is hypergraph to complete graphs of H. Is basically saying for each of those, I want to find subsets of that, comma 2 of H, catenate catenate that, and then I want to say undirected edge, don't I? Do I want to say undirected edge?
Yeah.
Okay, so let's try hypergraph to complete graph. Oops, to complete graph. Let's call that SSHH for no particular good reason. Okay. Seems reasonably convincing. Should we label it just for good measure? ACK. Okay. I
Okay.
think that looks fairly convincing. Now we say graph center of that. Oh, great.
Well, it probably doesn't matter which one of those.
Okay. So that's the genuine light cone.
Let's see, which one did we pick last time?
We didn't pick anything last time. We picked
We
it.
did.
We
We
picked it
picked
as
141.
yeah, 141. Is that in fact a valid one?
Well, let's check. No, it isn't.
Okay. So this here goes graph highlight. Let's map that over percent. Well, we can actually also just compute how many of the things there are there.
How many what?
Just a minute. GCCC equals that.
Probably shouldn't label them. And by the way, now that we have sub-hypergraph, we can just as well highlight the hyperedges as well.
Okay, so these are our deduced, we should do that, but these are our deduced I see. These are the effectively deduced light cones. I mean, these are the effectively deduced regions that we think we would have gone as compared to the ones we actually went, right? And in this particular case, the ones we think we should have got to are bigger than the one we actually got to. Do you see what I'm saying?
Yeah. Well, assuming the 3 there is correct.
How could it not be correct?
Well, because it depends on the rule size.
Why?
Well, let's say the output of the rule is so large that it like distance 10 across, you know, if looking at atoms.
Sorry, say that again. What?
Let's say the output of a rule is so large, then it's say, you know, distance 10 across, if you look at shared atoms. But according to the reconstructed one, or according to the light cone one, the distance would be 1 for any size of the output.
I see. I see. So we have to normalize. Okay. We have to normalize to decide our value of C. We have to normalize the number of steps. We have to normalize the sort of the average distance, the average reconstructed distance gone.
Yeah.
Which will effectively tell us the rule size. Well, some version of the rule size. Okay, so you're saying we can also highlight the hyperedges here. How easy is it to do that?
Well, it's very easy. Just instead of vertices, you put hyperedges and the graph highlight as lists. Or better yet, you join both of them.
Okay, so let's say so what do I do here? Instead of graph highlight, what do I do?
So join VVV.
Well,
And the second argument is a list of edges.
Which list of edges?
Well, the sub-hypergraph list of edges.
How do I get that? Expression.
Well, you have a hypergraph.
Yeah. So this is the expression spatial.
Yeah, put it in a variable.
Okay. Expression spatial hypergraph is this. Okay. Okay. So
right.
Okay. Now what?
So now where you have graph highlight is join VVV, comma sub hypergraph.
Hold on. Is VVV even the same? Oh, then you're saying I see.
Use a variable now.
I used VVV there.
No, I mean ESH.
For this.
Yeah, and in the VVV as well.
Okay.
Right, and then graph highlight join VVV is sub hypergraph of ESH, VVV.
How can this possibly work?
Why wouldn't it?
Okay, that's cool. All right, so here, this is the vertex list. Okay, so let's write this in a slightly more civilized way. So this is going to make effective spatial ball. It's an effective spatial ball plot, basically. Is that correct?
Yeah. Wait, which one is effective?
Yeah, which one is effective? Which one is effective? What the hell are we doing here?
Well, one is a ball.
Oh, genuine. That's the effective spatial ball from the genuine light cone. And this is the expression spatial. Okay, this is the effective spatial ball from the genuine light cone. And then we've got the reconstructed spatial ball. Right? Which one is the reconstructed?
Light ball.
Which one is the light ball? Yeah, wait a minute.
Light ball is the ball from the light cone.
Okay.
Well, at least they wouldn't get confused.
Okay. So let's go back up here. Let's define these functions again. Okay. So this is the two functions we're trying to use here. Definitions. Okay.
Is it a light cone or causal cone?
It's a causal cone.
Maybe it should be causal balls then.
Look, what it is causal cone spatial ball. Right? Deduce the effective spatial ball from the genuine light paren causal cone. right?
Okay.
Okay. So that's causal cone spatial ball. And then next is reconstructed. The next thing is reconstructed spatial ball. Okay, in which what we're taking.
Why is it reconstructed? It's just a spatial ball.
No, because it uses the
ordinary sense.
reconstructed. It's using the reconstructed structure of space. We don't know what the structure of space is.
Well, it's an ordinary structure of space using atoms.
No, this is the one using expressions, right? This isn't the usual form of space. This is the dual of the usual form of space.
Yeah, but uses atoms, not events, to connect those expressions.
So what are you saying? You're saying this should be called, I think it's still the reconstructed spatial ball because it's the one, well, okay, wait a minute. It's the geodesic spatial ball.
It's expressions ball. As the most natural ball, you can make other expressions.
Yeah, okay. Okay, it's the expressions spatial ball. Let's call it that. Deduced from function to construct balls in the effective expression deduced spatial hypergraph.
Well, I guess it's also an atomic ball.
Okay, all right. So hold on. Expression spatial ball. So that what does this take as an argument? This takes the center of the ball and the radius, right?
Yeah.
Okay. And by the way, this is everything that's being given here is this returns both these functions. Both these functions return expression indices, right?
Yeah.
Okay, then we're going to need a function. These functions take expression indices and make plots. Okay. Okay, so here, function to construct balls in the effective expression deduced spatial hypergraph. Okay, so what is, okay, so first we have the expressions. Okay, so that's the first thing we're going to do. So this is the ESH. Okay, so the ESH is just equal to the expressions spatial hypergraph of that. Okay. Okay, so now what do we do with that? How do we deduce the expression spatial ball from that? What do we do here to get that? We used what the hell are we doing here? We've got the hypergraph neighborhoods. What is this? What is this vertex list of this?
Well, that's what you want. Mm-hmm. Yeah.
What's that comma 3 there doing?
3 is number of steps or radius.
Okay, so then this, you claim, goes down here. This thing here becomes just ESH. This hash sign becomes the center. And this becomes
Radius.
radius. Okay, now we need one more function. Now we need a function to find the center of the effective spatial ball from the genuine light cone. Right? That's what we were using up here. That's where we had the graph center. So how do we do that? We're going to need subhypergraph as well. How do we find the effective spatial ball in the center? Okay, so it's this piece here, hypergraph to complete graph. Okay, hold on. So we have, what are we taking in here? Where's the effective spatial ball? What did we rename the effective spatial ball? Yes, that's the causal cone spatial ball. This is so freaking complicated. Okay, so this is now from a genuine light cone. All right. So this is a CCSB. So this is causal cone spatial ball center. Now, what information do we need? We need we might as well just give it WMO and X per 0. Right? So what we do is we compute subhypergraph of the expression spatial hypergraph. Okay, the effective spatial ball is the causal cone spatial ball.
Yeah.
Whoops. And that thing there is WMO. And that thing there, oops, I'm editing the wrong thing, is X per 0. Okay, and this thing here, I'm going to substitute it back in there in a second, is just WMO.
Yeah.
And the expression spatial hypergraph is still a thing. Okay.
Well, it's not the center yet.
No, I know it's not the center. I know it's not the center. Then we use hypergraph to complete graph of this. And then we say graph center of that.
Yeah.
Okay. All right. Now, what do we need to make plots? Okay, let's just give an example here. Let's do. Okay, so here, expressions, spatial ball of that thing. We're going to give a center and radius in a second. But to get the center and radius, we're going to use this with causal cone, spatial ball center. And there we're going to use expression 8 again. Oh, Christ. Why did that happen? Okay, let's echo the subhypergraph here. Well, that's weird.
Well, that's, I guess if it's disconnected, doesn't have a center.
So I think what we need to do then, if it's disconnected, I wonder if Graph Center has a way to deal with that. Let's just go through, okay, well, it's disconnected, so what can we do?
Well, we can find the largest connected component and find the center of that.
Fine, let's do it. How do we find the largest connected component? We just say, take largest by,
Well, we need connected components first. Just connected components.
it's not, it's, oh, no, we need graph connected.
It is.
No,
What
it's
is,
not.
there is no graph connected
It's
components.
connected graph components,
Oh, I see.
because otherwise it'll just give you the vertices. Okay, so take largest by connected graph components, comma, vertex count.
Right.
And then I want to say first of that. Take largest by requires a length. Why does it take the length there? Okay,
What is the length?
dandy. Okay, so then here, let's pick 31, for example, and let's go out distance 1. There we go. Okay, so now, important, drum roll. Okay, actually, let's do the thing to make plots, and then we'll do some comparisons.
Right.
And then I should go in a moment because I'm supposed to meet with somebody else. I know it's past your dead time. Okay, how do we make a plot here? We're making this plot. Where's our unordered hypergraph?
Right.
Where the heck is unordered hypergraph?
Here
Oh,
it
there we
is.
go. Okay. All right. And then that has a graph highlight. Okay. highlighted unordered hypergraph plot of ESH, comma, highlight. What the hell is ESH? Why isn't it ESH? It's just an H, right? H and vertices.
Right.
Okay, that is unordered hypergraph plot of H, comma, graph highlight of join vertices with subhypergraph of H, comma, vertices. Do you agree?
Yeah.
Okay, so now we say highlighted unordered hypergraph plot of an H. What is an H? So an H, where the hell do we get the hypergraph from? Where do we
Well,
get
we
that?
have another function to just get a hypergraph.
That was the expression spatial hypergraph.
Yeah.
Okay, all right. So then this uses, okay, so that there is construct the effective expressions hypergraph. Okay. Jose was going to join me. Okay, I just tell him to join. Okay, highlighted, unordered, this thing. So first we need to get the expression spatial hypergraph. Where's this thing here? Okay. Expression spatial hypergraph of this. And then it's the causal cone ball center, for example. Okay, so this is the expressions hypergraph, and then that is, okay, then we say unordered hypergraph plot of that. And now we would say of this thing, that comma, causal cone, spatial ball center. What the hell do we need here? We want the spatial ball.
It's a special ball. Hold on.
Yeah, it's a spatial ball of that thing. No. It's the expression spatial ball. No. Causal cone spatial ball of that, comma, expression 8, for example. Okay, there we go. So that's showing the effective That's showing the genuine light cone. That's the genuine light cone intersection. Light cone intersecting the reconstructed spatial slice.
Yeah.
Right? And now we can compare that with the deduced geodesic ball of a given radius in the reconstructed spatial slice. Okay, so what that is, let me see, that's the same thing. So for that, we need a causal cone ball center. Instead of this, we need a expression spatial ball, right, with a certain radius, okay? So expression spatial ball of that, and then the center is a random choice. Let's say random choice. Well, let's not do that. Let's just do first of the causal cone ball center which then recomputes the causal cone. Okay, now we have the radius, let's say 1 or something. First of that. That's the causal cone ball center expression spatial ball. Is that right? Okay, what did we get wrong here? Highlighted unordered.
Is it a pattern there in the ball center?
So that's the effective spatial ball. Okay, the reconstructed deduced spatial ball. Okay, so let's try it another couple of steps. Okay, so this is now, let's go 7 steps here, okay? Oh, for goodness frigging sake. That expression was too close to the, I mean, yeah, let's just try expression, I mean, we can just, there'll be expression 30. Let's just try that. Okay, I picked that expression at random. So let's go here. And now let's do the corresponding thing with expression 30.
With 7 steps here as well.
Okay, so that's radius 1. Then this is radius 2. Okay, so this again is genuine light cone. And this is effective reconstructions. And I don't know how many steps we think we have to go here. Let's try one more step just to see what happens. I mean, I don't know what expression number we should try. Let's try expression 70, and let's go 8 steps. Let's go 9 steps. Wow, look at how similar that expression graph looks to what we're used to. So
Well, it
that's,
should be.
I know. It doesn't really matter whether it's which one it is. Okay, so in the limit, those are the same. Okay, so now here, 9 steps, and then this would be 9 steps with expression 70. We don't really know how many. I mean, we really need to plot as a function of it's very hard to interpret this, because really what we should be doing is just to measure the size of the light cone what are we trying to do? We're measuring the size of the light cone as a function of number of steps. Right, in one case, we need to know, how do we pick an expression on a particular layer?
Well, we can check. Well, we can check generations of expressions.
Yeah, but
take
okay,
all
fine.
positions and take random choices.
Okay, but so what we want to do, really what we want to do, workflow. Pick an expression at a particular generation, right? Then see how its genuine light cone expands and compare it with the sizes of reconstructed spatial balls. Spatial balls with certain radii. Right, so as we evolve forwards for the genuine light cone, it's going to get bigger. Right? The number of expressions in the genuine light cone is going to expand.
Yeah.
And the reconstructed spatial balls are also going to expand, but those reconstructed spatial balls, and so we want to compare those two things. Now, unfortunately, this is an aggregate thing, and the true sort of Maxwell demon, you know, the demon navigator, I've got to come up with a better name for that. What should we call it? Well, we need a name for the little space navigator. That isn't really the right term. It's not a space navigator, it's a subspace navigator. What's that?
Right.
Or a subspace demon.
People will misinterpret that
Who? What?
if they know Star Trek.
But isn't this the same thing? Isn't subspace communication exactly this type of concept? I tried to look this up in Star Trek, you know, fan sites. I mean, yeah, anyway, so okay. Okay, so anyway, but the problem is that this is an aggregate light cone, whereas what we imagine is that you need one of these subspace demons to jump from edge to edge to make this work. But still, something might happen. Oh, I see. Actually, yeah, right. So, I mean, the total size of these light cones Yeah, I don't know what shape these light cones will be. Jose just joined us, and actually, I wouldn't mind just maybe we can wrap with Max, but just explain to Jose what we just did, because Jose, that's a good test of whether we know what the heck we're talking about.
Okay.
Are you with us, Jose? Or
sorry. Yes, I am now.
okay, all right. So we've just been trying to invent subspace demons. Okay, let's explain to you what we did. It's all right. We don't have to go through everything here. A lot of this is irrelevant. Okay, so this is okay, this is relevant. Okay, so this is a graph that represents the evolution of one of our systems. But what's happened here is this is a spatial, this is a hypergraph. This is a representation of a hypergraph, except that the individual hyperedges are indicated with nodes here. Does that make sense so far?
Okay.
And these individual hyperedges, with this rule, pairs of hyperedges are combined with events. Okay, that's an event, right?
Yep.
And so this is a light cone starting from an event, right? That is
Expression.
an expression, sorry. That's a causal cone of what events and expressions can be affected by that expression. Make sense?
I'm not sure what expression is here.
Okay, so
It's a hyperedge.
It's a hyperedge. These things, these bluish nodes, they are expressions of the form, 3, 4, 5 or something. Ignore when I said 3, 4, 5. Just ignore the fact that those are called 3, 4, 5. Those are different numbers. Those are indices for the hyperedges. The hyperedge contains certain elements, atoms of space, whatever you want to call them, in the hypergraph. But each node here represents a hyperedge in the hypergraph. Okay, so then these are combined. Okay, those are events. Okay, so this then is the light cone associated with one of these expressions. This is, if you were to attach your subspace demon to that expression, this is sort of where the subspace demon could go, if that makes sense. Okay, so now what we're going to compare is the actual places the subspace demon can go versus, okay, so this is the actual places it can go. All right, now let's say we're trying to reconstruct space. How do we reconstruct space? The answer is one way to reconstruct space is to simply look at these expressions down here and say, how are these knitted together to make space? Answer, they are, let's see. Max, now I'm confused. Oh, no, I know what the point is. That each one of these hyperedges contains certain elements, but different hyperedges may contain elements in common. Okay? So we have another picture somewhere here, this picture here, that says how the hyperedges, what elements the hyperedges contain. Okay? So this is what we're going to use to knit together hyperedges to make our version of what we think space is. That makes sense?
I think I'm following. I don't see the full construction yet.
Okay. The alternative would be to do the construction using events, Max. That would be the alternative way to reconstruct what we think the structure of space is.
Yeah.
And that's not equivalent in general.
Yeah, it's not.
Okay, so we've got two possible reconstructions of space. One is from knitting of hyperedges, and the other is from knitting of hyperedges by elements, and the other is now I'm confused. Oh yeah, the other is knitting of hyperedges by events. Now those are related, but they're not the same. Am I right?
Yeah.
And they're not the same because of the flow of hyperedges, the flow of elements through hyperedges isn't precisely just mapping causality. I mean, causality, it implies causality, but it isn't the whole story necessarily. Okay, so anyway, so let's go on with what we did here. Okay, so now this thing here is a typical reconstructed oh God, this is such a complicated thing. Okay, what this is doing is it's reconstructing a hypergraph. Oh my gosh, this is
It's
a
a dual of a
hypergraph.
spatial graph.
What's that?
It's a dual of a spatial graph. It has hyperedges expressions on as vertices, and
Right.
they are connected in the hyperedge, so they have shared atoms.
Right.
So
From
each
knitting of
atom
hyperedges by
corresponds to a
elements.
hyperedge in here.
So the reconstructed object is the dual of the spatial hypergraph, i.e., its nodes are the hyperedges of the spatial hypergraph, and its hyperedges and each hyperedge records, each hyperedge represents the locations, represents, hyperedge is associated with a single element, single atom, space atom, whatever we call them. Okay, so that's possible. Okay, so that's a reconstruction of space, Jose. Does that make sense?
I think I'm following.
Okay, so now the big question is, what is the comparison between the region in that reconstructed space that we reach from the actual causal cone, from the actual light cone, versus what we reach by just making a geodesic ball inside this reconstructed space? Does that make sense?
I think so.
Okay, so then the claim is that the speed of travel is the comparison between those two things. The speed of travel, you could travel faster if the causal cone reached further than the if this causal cone could ever reach further than the reconstructed geodesic ball, then you could travel faster, right? Now, there's a trickiness here because the speed of light is an arbitrary thing that you determine by looking at the average comparison of this causal ball, of this causal cone with the geodesic ball. That's how you determine the speed of light, because the speed of light will depend on the size of the underlying rule. this making sense?
Yeah.
Is Jose following this?
I'm having trouble imagining why that could happen. So the ball is going to reach out like, I don't know, 4 steps in the graph.
Yes. Which ball? The geodesic ball on a particular spatial slice.
Yes. So that will be determined by a number of steps. That's the concept of the ball, right?
No. Well, different steps. Okay, so we've reconstructed the spatial graph. Okay, and now as purely as a matter of geometry, we're going to say how far does the ball go out.
Right.
Okay, it's just geometry. There's no dynamics anymore.
Yes, by steps, I think I meant edges. So you start from a vertex and you count edges in all possible directions from that vertex.
Yes.
Right? That's the ball.
Yes, that's right. So now the question is, could the number of edges that you go that way be fewer than the number of edges you can reach by going out in this causal cone from something sort of above it in the I mean, in this causal cone, if we drew this light cone, can we do that? Can we draw the? We can't draw. We can only draw the intersection of the causal cone with the final state of this WMO thing, right? So, but if we drew the previous states of this, we would see this light cone expanding, and we could compare the expansion of that light cone. Oh no, that doesn't work because those expressions simply don't exist, right, Max?
Yeah, the previous step of expressions don't exist here.
Right. So what Jose is asking is there a theorem? Could there be a theorem that says that the distance you can reach in the geodesic ball is always not less than the distance you can reach in the causal ball?
It might be simpler. I mean, is it possible to advance 2 edges in a single step in the causal structure?
Well, yes, if the rule is large enough.
Well, let's assume it's a one-level rule. It's completely unobvious to me how far you go here. Boy, this is hard to understand. How far you go here, because you haven't even constructed, at the time when that causal cone is being formed, you haven't even constructed this final spatial hypergraph. Right? That final spatial hypergraph is constructed from what's generated from the evolution. Oh my gosh, I don't understand this.
So you can definitely go farther in the atoms ball.
What's an atoms ball?
Than in the causal ball. Oh, the atomic ball. What is this? Expression spatial ball. Yeah, this one. So you can go farther in this one in some cases than in the light column, because shared atoms doesn't imply the shared their events. Because, for example, you might have you can have 2 different rules. One operates on binary edges, one operates on ternary edges, but they have shared atoms between them because of initial condition, for example. And there would be some distance between binary and ternary edges because of shared atoms, but the events would never touch both of them simultaneously.
I'm not understanding this, but I believe you. Okay, one can go further in the expression spatial ball.
Well, one
Well, it's
might go further.
one might be able to go further. One might be able to. One can potentially.
In some cases, one can go further.
There exist rules that make one be able to go further in the reconstructed spatial ball versus the causal ball.
Right.
And can you just characterize for a second what kind of rules those are?
Well, if basically what you want is to have expressions which have shared atoms, but no rule matches those expressions simultaneously.
I see. Expressions with shared elements are not both matched.
Yeah. But let's see if we can have a reverse. So can you go further in the causal ones and reconstructed one? Well, yes, because it might disconnect spatially, for example. So if you have
Yes, that's right. Okay, so wait a minute. So this is the case. Speed in space.
And it might disconnect, not entirely, but it might remain connected through other chunk of space far away, in which case one of the ball will be, well, it will be disconnected. So it's not the same as larger, but
well, okay. So
no, it will be large. It will cover, right. So yeah.
So what are you claiming here?
So
this is the moment when warp drive gets invented. Okay, go on.
Well, anyway, the rule might disconnect its inputs into separate pieces.
I see. Could disconnect its inputs, which means
a spatial ball will go to
right, which would limit how far the spatial ball could extend, but the causal ball would extend. So that the case,
right, because we'll pick one of the spatial balls to cover some of the resulting.
Right. But so this is like a black hole. This is like, analogous to.
Why is it a black hole?
Well, because there are two different. What this is saying is you're disconnecting in the spatial ball, but the causal ball. So you can go into one of two black holes. And what this is saying is you don't have a way to explain I'm now confused. I think that's right, though.
Well, I wouldn't say that black holes necessarily. They just cannot communicate with each other anymore.
Well, okay. So wait a minute. This is saying that you're saying you can reach, i.e., you can causally reach more places in space than you can geometrically reach if space is broken by event horizons.
Yeah.
But okay.
Yeah, I mean, if one of those is a black hole, that would be a special case of it.
Right, but the question is, okay, that's an existence proof.
Yeah.
That you're saying that there is what we attribute to be a certain distance in space is limited inside the horizon.
Yeah. Yeah, so the way it will look like in real life is that if you had a wormhole before in the past, and then you created some stuff on both sides of it simultaneously, and then the wormhole disappeared. And now it looks like you communicate faster than the speed of light because you have objects on two different areas of space far away.
Why does the wormhole disappear? Oh, you're
Well, because
saying
if it doesn't disappear, there would be a spatial ball through it as well. And then it
I
wouldn't
see what
look
you're saying. I see what
faster
you're
than
saying.
light. It would
So
just be
this is analogous to having a temporary wormhole that then disappears, but leaves the results of its communication.
Yeah, I guess what we would really want is that both the past light ball and the future light ball are larger than the atomic ball.
Okay, so claim,
I'm not sure if we can make that.
want both the past and future causal balls to be bigger than the geodesic ball, than the instantaneous geodesic ball.
Yeah,
Geodesic ball.
because that means the wormhole wouldn't disappear.
Right, so we want the
Suppose we can
projected
have two
causal ball.
wormholes, but that's, well, actually we can't because the rule would have been disconnected.
Past and future causal balls.
Yeah, I don't know if you can do that because in order to create future, actually we can't in a significant way because in order to create a future causal ball, we need to be able to match rules to the future, which would connect expressions. But the only way to do it, if they're connected by atoms, because the connected rule wouldn't match them otherwise, which means the future causal balls are actually much more similar to atomic balls because they use expressions that already exist to determine if they're causally connected in the future or not. And that's also what you're going to use if you're going to travel, because past causal ball doesn't, I mean, the past light cone doesn't exist anymore, and the future light cone is what you're going to go to.
Yes. Wait a minute. So you're saying, what are you saying here? You're saying future.
And then future causal balls, first of all, seem to be more useful here, because that's where we're going to travel.
What the heck is a future causal ball? I.e., something.
It's a causal ball for
which generates.
future.
Right. Something, i.e., something that will reach a particular event, a particular expression in the future.
Yeah. And so that's connected to the geodesic ball, because in order to get to some common expression, you have to match those current expressions in the geodesic ball. But in order to match them, they need to be connected through atoms.
Okay.
Which means geodesic ball would be larger than causal ball, roughly speaking.
Well, the question really is it always larger or is it simply statistically larger?
Well, it's always larger given certain, I mean, if you multiply by the rule size properly and so on, it will always be larger because you have to, I think, because you have to match nearby, you can only match nearby expressions, atomically speaking, with a single event.
Okay, so possible claim which I don't believe, but anyway, possible claim. The causal ball is always strictly smaller than, it can never be larger.
There is a constant such that the causal ball would be always smaller than this constant times.
There's a constant, say C, for which the causal ball is always smaller than, for which the causal ball for an expression t steps in the, for which the future causal ball for an expression t steps in the future is always smaller than the
atomic ball times
CT step geodesic ball. Right. So if that was true,
but the reverse is not true.
That what?
That you might have geodesic balls that are larger than causal balls because, again, its events might not just be able to match some of the expressions which are nearby.
Okay. You might have a geodesic ball that is larger than the causal ball.
Yeah, arbitrarily larger because some pairs of expressions just cannot be matched by an event, even if they are atomically nearby.
You can have geodesic balls that are larger than causal balls because, and that's the case where you have a horizon. Is that right?
Is it a horizon?
I think so. You can't match across it.
Well, I guess. But you might not be able to match it, or just maybe more difficult, so that you need more steps to do it, or something like that. So it's not necessarily a horizon.
Okay, because
it's just basically, if you have a rule that matches everything, any group of expressions, and the only thing it needs is that there are shared atoms in them, then that rule will do exactly the same thing as a future causal ball. Oh, no, it will do exactly the same thing as geodesic ball, because it will essentially just take the geodesic ball and like directly construct a cone.
I see. So basically the claim would be, okay, a rule that matches any collection of edges, collection of hyperedges out to a certain geodesic distance.
Yeah.
Will simply reconstruct a geodesic ball.
Yeah.
By definition, actually.
Right. And the real rules would always make it smaller because there would be subset of that.
That's a shame. No warp drive.
Well, I wouldn't be so sure because there are other options for warp drive. I mean, there is well, first of all, we can, if we travel there first, we can always build a wormhole. And the second, there is a possibility we could have a spore drive.
What?
I
What?
guess you watched the new Star Trek. Well, basically, they have a, what they call a mycelial network. Basically, you have a network which lets you travel to arbitrary place in space instantaneously, which essentially means you have a network of long-range connections on top of ordinary space, which are probably sparse enough so they don't, so you can't see them, but you
that
can
could
still
exist
catch them.
from the beginning of the universe, right?
Yeah.
Okay, so there's a pre-existing network.
Yeah, so that's at least 3 different cases. There's a pre-existing network. One can make a network,
Right.
which is still useful.
Pre-existing network one can construct, and dynamically constructible. Just in time. JIT.
What do you mean just in time?
Well, that you're actually exploring the network as the network is built, because as the network is built, you pick a direction in the network, just in time network construction.
Well, that's a special case of network one can construct.
Well, okay, this is basically navigating through a network that is otherwise being constructed.
Sure, but if you're navigating it while it's being constructed, you're not going faster than the speed of light.
That's not at all clear. That's not at all clear. It
Well,
depends
what do you mean?
No, it depends on the... Look.
The whole point of constructing a network.
No, but we're not navigate. I'm not talking about this kind of network. These are big networks, okay? Navigating through. I shouldn't call it this way. It's the dynamic case, okay, which was the one we've been considering so far. I shouldn't say network. These are pre-existing network of wormholes, basically, is what you're saying here.
Yeah.
Wormhole network one can pre-construct. Okay, and the dynamic case is a case where you're not really constructing wormholes at all. What it is that space, the thing you deduce to be space, is smaller than the thing. I mean, this is the thing that you claim might not be possible here, because you say any rule that this is the maximum case, right? Any rule that matches any collection of hyperedges will go out to a certain, will reconstruct a geodesic ball, but that...
Well, assuming the rule is connected.
Oh, yeah. Assuming, okay, fine.
Which I guess it doesn't have to be, technically speaking.
Okay, but then, okay. We'll reconstruct that geodesic ball. So then the causally constructed ball, which is the past light cone of that future event, right?
Yeah, there'll be a sub ball.
Okay.
Well, there's also fourth case where you manipulate the updating order so that the part that's moving is getting updated more frequently than the rest, which I guess would be probably the most similar to the warp drive, although I don't really know how it works exactly.
No, wait a minute. So final case is manipulate update order.
Yeah, so that the part around the warp drive, the part of space around the warp drive is updated more frequently than the rest of the universe.
Right, brother. So that the space around where you are is updated faster than space further away.
Right.
But that manipulation of updating orders has to be sort of a quantum. It's either a reference frame story, which I don't think can be real, or it's a quantum story.
Isn't there a way to do this warp drive if you have like negative energy or something like that?
There is, and Jose just made a nice notebook about that. There it is.
Right, so that's probably what we need here.
Well,
I mean, if it's possible in GR, it has to be possible in
this
our model too.
Right, with negative energy, with negative mass, and negative mass is just an absence of negative mass is a decrease in the number of causal edges ahead of the thing.
That means it's updating more rarely.
Ahead of it, it's updating more rarely, yes.
Interesting.
But so what that would mean is, see, that means somehow in the causal graph, see, I don't understand how you avoid this problem, right? Because the notion of what space is, but this may depend on reference frames and things.
No, you don't avoid this problem. You are still moving with the speed of light. It's just, let's see.
No, it doesn't work because remember, this is the exact same thing. We've got a model of space now.
Yeah, but it doesn't say what the updating order is. Because the question is, what is time?
Yes. Well, time is determined.
The time could be different.
From why? For what? When? Where? What?
Well, let's see. Well, one thing is it's obviously true. In some models, you can have, you can just make an evolution order which would just move a particle somewhere without touching anything else. In this case, from external observer's point of view, it will look like it's moving faster than the speed of light.
Yeah, but not from an internal observer point of view.
Well, from an internal observer point of view, it will look like the rest of the universe is frozen.
It won't look like anything. You can't even sense the rest of the universe because the only way you know what's happening is through the causal graph.
Right, which is what it means to be frozen.
I don't understand how the causal graph
Things
can
are
be frozen.
changing slowly. Well, you don't interact with it. I mean, you interact only with part of space where you want to move. and the rest of the universe is not doing anything.
Look, in some sense, that's a gravitational redshift here. In this case, the metric, I don't even know what this is. What is F here? Jose, what is the gravitational redshift around this thing?
Gravitational redshift. So that graphic there is representing expansion. So what's happening there is a sphere. The negative energy is close to the surface of the sphere. The interior of the space is essentially flat, and you put something inside. And this is moving along the x-axis towards the right.
Mm-hmm.
And the negative energy is kind of removing space from the front and expanding the space on the back. And by removing and expanding, we have to think of inflation, a universe expansion, this type of thing. So space is being created. Things are not moving in space, it's just the space being created.
Right, but that's easy to do in our models, to have space being created. But what that's saying is that if we look at, you see, that's exactly what we're trying to do with these things here. This is what, space being created. What is the analog of that? The analog of that is let's see. Space is being created. So naively, the way that would work is if there's a higher density of nodes, that is the creation of space. That will be further in space, right? You create a bunch of nodes. That's going to extend space at that point. Right? In other words, if I have somewhere, if I'm, creating space, right? If there is a higher density of nodes, created in a fixed number of steps, which might not be possible, created in a fixed number of steps, there's a higher density of nodes than usual, created in a fixed number of steps. I think that means, yes, I think that is effectively negative energy. Because what that's saying is, well, it's negative relative energy. Because what that's saying is that for a fixed number of causal, that can't work. For a fixed number of causal edges, you're generating a larger region of space, which means the density of causal edges is lower. If that makes sense. I'm confused by this. I have to say, I'm confused. But so in this model, so if I were to plot time in this model, what does time do as a function of position here?
So you have to think here of a sphere. So think of the x-axis, which goes towards the right. And then this is a section. So this is cylindrical around the x-axis. So this is just, this rho is kind of the distance to the x-axis.
Yeah.
So this sphere has, the next plot is a plot of minus the density. And you see how I was expecting that the energy would be localized in the front and back parts,
yeah.
but it's mostly localized on the sides, which is interesting. So that's minus, right? That's minus the energy. And,
okay.
And this is just moving constant speed towards the right. Now, I must say that I hadn't read the article before. What I've discovered by reading the article of Miguel Alcubierre is that he plays the standard trick of, rather than specifying the matter and solving for the metric, he just manually constructs a metric with some characteristics he wants, puts it in the Einstein equations, and then he gets the matter that will produce that metric, which of course it's a crazy matter, but he doesn't care. So the metric is manually constructed. The interesting thing is that there is a metric that can do this. This isn't the interesting thing.
What is the statement about? Given a metric, can you construct matter that will make that metric?
Yeah, so the Einstein equations is, you can read them as second derivatives of the metric equals matter, T mu nu.
Yeah.
So the standard thing to do is you provide the matter with the properties.
No, I understand, but I'm asking the inverse problem. What does the inverse problem look like? That is, given a metric, can you construct matter? Can you set up matter that will produce that metric?
Right, which is something that people do, but it's considered cheating, because in the vast majority of cases you will get non-physical matter, of course. It's
okay,
like
so,
saying,
but so what you're saying is, in the Einstein equations, you know, given a metric, there exists a T mu nu. It's kind of obvious that this must be true. Exactly. There exists a T mu nu.
Yeah, that corresponds to that metric.
That gives that metric.
Exactly.
The issue is whether the T mu nu is realizable.
Exactly. This is cheating. We could say the same thing of the Newton's equations, right? We just take a crazy trajectory, differentiate it twice, we get the force that would produce that trajectory.
Yeah, right. For Newton's equations, right, so the question here is, our effective T mu nu, so our T mu nu is determined by the distribution of causal edges. That's what constructs our G mu nu, basically. And for us, again, there is dynamics to what conceivable causal edges there can be. But I mean, the fact is, there's nothing that says that our version of faster than light travel has to respect Einstein's equations. Nothing that says that. I mean, in other words, you can have a limit in which you get Einstein's equations, but it might not be the case that the individual, it's like my analogy with the gas demon as well as the subspace demon, the Maxwell type demon, the gas demon that has that just hitches a ride on the right molecule. The question is that something we can do here, or is there a reason why hitching a ride on the right causal edge can't work? If you hitch a ride on a causal edge and you say, where will that take me? Could that causal edge ever take you further Wait a minute. This argument about geodesic balls is not correct, because there's a scaling factor, which is the critical scaling factor. That is a scaling factor between the average causal ball and the average geodesic ball. And the question is, does there exist a fluctuation in the causal ball right? So the average, this isn't right. This isn't right. So this is
Not the
saying,
average, it's a rule size.
well, it depends if there are multiple
The
rules.
geodesic ball I'm talking about has to do with the rule size. So for the constant C here, it's for each causal ball step. It takes the number of steps in the geodesic ball, which corresponds to the diameter of the rule. In which case, geodesic ball will always be larger.
I'm sorry. Wait a second. What are you saying? You're saying, no, I'm saying that the effective, okay, the geodesic ball is determined by running effectively an anything goes rule.
Right, but anything goes rule needs to have a certain radius or diameter. If you pick diameter of the anything goes rule the same as diameter of the input of the ordinary rules, maximum of diameters of the ordinary rules, then geodesic ball, the rule for the geodesic ball
Will always overgenerate the causal ball. Right?
Yes.
It will always go further than the causal ball.
Right.
But you won't attribute, look, if the causal ball, for whatever reason, only goes half as far because of some symmetry condition inside the causal ball, the effective speed of light that you will deduce will only be half the size of the geodesic ball. So I'm saying you've still got a conversion between the number of steps that you go in making the geodesic ball and the number of steps you go in making the causal ball.
Okay.
Right?
That's
So what I'm
true.
arguing.
Well, it is possible that you might have a situation where almost always the realistic speed of light is smaller than the one you will get this way.
Exactly. That's the point. So the question is, are we
But
in
there
that
is upper
situation?
limit on the speed in any case from this condition.
Oh, I agree with that. Yeah, I agree with that. The question is the actual speed of light, i.e., this gives an absolute upper limit on the speed relative to the geodesic speed relative to what we can call the geodesic speed. Well, this is the geodesic speed is the absolute upper limit.
Yeah.
Because it's the anything goes rule, which has to be able to go faster than anything else. Has to be able to, get further in space than anything else does, sort of by definition. You know what? That's not necessarily correct. It's not correct because it makes its own space. So the anything goes rule will be making all gobs of the rule does. So the anything goes rule will be making gobs of extra space. I don't think it's obvious that I don't think this argument is correct. Jose, I'm curious in Okay, a couple of questions. I mean, in standard relativity, assuming that we have negative mass, we don't have much trouble getting all kinds of wormholes and things like that. Is that true? By negative mass, we break the singularity theorems by having negative mass. And so we can get redivergence of GD6,
Right.
even if they converged, right?
Yes, but it has to be distributed in the proper way. So it is not, for example, in this Alcubierre's drive, the negative matter must be in a very particular position.
Yes.
Otherwise, it wouldn't work.
Right.
This is what we were saying before. For example, the fact that this is asymmetric in the sense that in the front is contracting space, in the back it's expanding space, is kind of incompatible with the symmetric distribution of the negative energy in the next diagram. So what happens here is that this starts working once the sphere is moving. So, and the article is explicit about that. So the sphere must have some rockets. It starts moving, and that generates the asymmetry in the direction of motion.
I see.
And then it starts working.
And then it can start making space in front of itself.
Exactly.
Wait a minute. No, it makes space behind itself. Is that right?
Behind itself, exactly. It's contracting it in front and expanding it behind.
Again,
So
but what happens to time? What happens to somebody inside this sphere, inside this cylinder? What is their time relative to people outside?
Well, the metric has that. I don't know. I would have to analyze the metric there.
Okay. That would be interesting to know. What happens to time for people moving inside the bubble?
Right. My prediction that I have to make sure is that the times in these metrics are the same. I mean, the observers inside are not feeling anything. They are
right. I think you're right. I think the time is going to be unchanged, but then it's unclear what it means to say that. I mean, basically what's happening is that it's like you're walking on a treadmill, and instead of going forwards on the treadmill, you're just making more treadmill somehow. But how does that work? I mean, how does it work relative to the rest? I mean, does the thing actually appear to move with respect to the rest of the universe?
Yes, it does. Yes. So this is like two galaxies in the expanding universe, right? So the other galaxy seems to be moving with respect to us, but it's not really moving with respect to space. It's just the space in between us that is expanding. And so our times are the same. It's just the cosmological time, which is the same for everybody.
Yes.
Just that, and you see, because the space is expanding so much, there are galaxies that are receding from us at speeds which are larger than the speed of light. And that's the same thing is happening here.
Well, hold on a second. Analogous to expansion of the universe, where effectively space is created.
Exactly. By expansion.
Right. But so explain that to me in terms of in the standard metric, FRW metric, right? How far away? I mean, in practice, there are not galaxies seen above redshifts of like 5 or something, and a redshift of 5 is well below the speed of light. But it isn't the no. Wait a minute. If there's a galaxy effectively receding at above the speed of light, that means there's an event horizon between us and it.
I wouldn't call it event horizon. There are cosmological horizons.
Okay, it's a cosmological horizon,
particle
right.
horizons. They have special names. There is a horizon, but it has special name.
Right. So it could be moving away from us at a higher speed, but there is a horizon.
Yes. So there are Hubble horizons. I don't remember all these possibilities. There are nice diagrams out there with all these diagrams. But yes, it's true that there are galaxies that, for example, we were seeing in the past, but because they are receding, there will be a moment from which we will not see them anymore.
Right.
And then they are totally separate from us forever.
Okay, so the analog of that in these models is that there is no causal path from that galaxy to us. Then in the causal diagram, there is okay, so the formation of a cosmological event horizon is simply a disconnection in the causal graph. That's what that corresponds to, I think. I don't think, I mean, I don't know. Yeah.
Another important thing of Alcubierre's solution is that it's purely local. It doesn't require topological changes like the wormholes. It both use negative energy, but in a very different way. So this is, in a sense, this is less exotic than a wormhole.
Right. Yeah, I understand. It does not require topology change. That's why I strongly suspect we should be able to get such a thing. I mean, we must be able to get such a thing in our models. And the question is, what is the signature of that at the level that we're looking at? You know, at the level of these kinds of things, what is the signature of this phenomenon? Do you see what I'm saying?
Yep.
I think we need to understand things like time dilation and so on. I mean,
but time dilation is
gravity.
Purely, no, but time, we do understand that stuff, but it doesn't, the question is, can we see this phenomenon below the level of those things? Because time dilation comes about because of the different reference frames that we might use. Well,
we can see it in special relativity, but can we see it near a massive object, for example? I mean,
we have to pick the frames. We have to pick what reference frame we're using. Right, and what we're doing we're picking what we think is the cosmological rest frame. But I mean, that's a question of our perception of what's going on, right? It's not...
Right, but do we have any examples of where we actually have a massive object which...
No, we do not.
So I guess that's what we need to make in order to understand this stuff.
Right. All right, we should wrap up for now. Tomorrow I am supposed to be giving this colloquium talk about these topics. And Jose, if you're available, it'd be wonderful if you could come and fish me out of horrifying problems.
What time is that? I have a busy morning. What time would that be?
Let me look. It is at 1 p.m. Eastern.
1 p.m. Eastern.
Which would be noon Central.
Right. Well,
and we'll go for 2 hours. So if you're able to drop in partway through, you can fish me out of the difficulties I've got myself into.
So I have my the weekly geo meeting at noon exactly, and we are discussing important things. So I think I have to attend that. But then after the meeting, I can attend.
Okay, great.
So I think the second hour, I can be there.
Great. That's great. All right. Well, we haven't solved the problem, but we're making some progress here. It's a little difficult to understand. Again, I am certain that there is a microscopic version of this phenomenon that we should be able to see just in terms of light cones and this and that and the other without going all the way to continuum metrics and so on. All right. Well, I should go. Thanks a lot, guys, and to be continued.
Okay, bye.
Okay. Bye-bye.
Yeah.
See you, Max. Bye.